Right. In this lesson, we are going to break down how reinforcement learning can be used for inventory management. We'll start by looking at the problem itself, why inventory decisions matter, and what challenges come with uncertainty in demand. Then we'll go through how an RL agent learns to minimize costs by making better stocking decisions over time. You will see how the training process unfolds, how the agent improves, and most importantly, how it compares to a traditional inventory policy. By that, you will have a clear understanding of why RL is a strong alternative to fixed decision rules and how it can lead to better cost efficiency in real-world applications. Let's get started. You can see our libraries here, and I will pass. And here what we are looking at is initialization of the advanced inventory Q-learning agent class. So this is where we define all the key parameters that shape how the agent learns and makes decisions. First, we have the environment parameters, and these define the structure of the inventory system. The agent is working with max inventory, sets the upper limit on how much stock we can hold at any given time. And demand lambda controls how unpredictable demand is. It's based on Poisson distribution, which means demand varies but has an expected average. Then we have cost holding and cost shortage, which we define the penalties for storing too much inventory or running out of stock. And we have the learning parameters for Q-learning, and these are what determine how the agent balances acceleration, trying out different strategies, and exploitation, sticking with what it has learned works best. And discount is set to 0.9, which means the agent values future demands almost as much as immediate ones. Alpha is the learning rate, controlling how quickly the agent updates its knowledge base on new experiences. We start with a relatively high learning rate of 0.1, but it gradually decays over time using alpha decay. So as training progresses, the updates become more stable. And we have epsilon, which controls how often the agent explores new actions instead of following its current best quest. At the beginning, epsilon is set to 1, meaning the agent explores completely randomly. But as it learns, epsilon decays down to 0.01, so by the end of learning, it's mostly following what it has learned to be optimal rather than making random choices. And okay, the agent is going to train our episodes, you can see, which is set to 3000, and this means we are running 3000 complete simulations of the inventory environment, allowing the agent plenty of opportunities to learn. And each episode has a maximum of 200 steps, meaning that in every training run the agent gets up to 200 inventory decisions to adjust its policy. And after defining all these parameters, the agent initializes an empty Q table, and this table will store the values of different state action pairs, which is the core of Q learning. At the beginning, the table is empty, but as the agent interacts with the environment, it fills up with values that help it make better decisions. And finally, you can see we set up two lists, episode cost and rolling average cost, to track performance. And these will help us see how well the agent is doing over time, whether the costs are decreasing and whether the training is working as expected. And okay, let's continue. Here we have init Q, which is responsible for initializing the Q table. And the Q table is where the agent stores what it learns about different states and actions. It covers all possible states, which are combinations of how much inventory we have on hand and how much is already on order. Then, for each state, it assigns an initial random value to every possible action. The agent starts with no knowledge, so it just fills the table with random values and updates them as it learns. Look at here, we have get demands, and this function simulates the randomness of customer demand by drawing values from a Poisson distribution. Demand is not fixed, it fluctuates, and this is what makes inventory management tricky. By modeling demand this way, we are making sure the agent learns in a realistic setting. Okay. Okay, and now environment step is where the environment actually updates based on the agent's actions. The agent starts with a certain amount of inventory and some incoming stock. Then demand arrives and the agent sells as much as possible, either the full demand amount or whatever it has available. After that, we calculate costs, and if there is leftover inventory, we apply a holding cost. If demand exceeds supply, we apply shortage cost, and the reward for the agent is simply the negative of this cost. So the lower the cost, the higher the reward. And finally, the next state is determined based on what's left in stock and the new order decision the agent made. Okay, and last function for this part here, what is that? Choose action. It determines how the agent picks its next move. It follows an epsilon graded policy, which means that early in training it makes a lot of random decisions to explore different options. But as training progresses, it gradually starts relying more on what it has learned. If a random number is lower than epsilon, it picks a completely random action. Otherwise, it selects the action with the highest Q value, the one that it believes is best based on past experience. And okay, sorry, let's stop here. Here, update Q, which is where the Q learning update happens. This function adjusts the values in the Q table based on the agent's experience, and the update formula follows the standard Q learning you can see here. So what's happening here? Actually, first the agent looks at the next state and finds the best action it could take based on its current knowledge, and that's best next action you can see. And then it calculates the target value, which is the immediate reward plus the discounted future reward. The difference between this target and the current Q value is called the temporal difference error. The agent then updates its Q value by adding a fraction of this error controlled by alpha, the learning rate. This way it gradually refines its understanding of which actions are best. Okay, now let's move on to the train. This is the main training loop where everything comes together. The agent runs through a set number of episodes, each one representing a full simulation of the inventory system. At the beginning of each episode, it starts with a random initial inventory state. Then, step by step, it picks an action, interacts with the environment, receives a reward, and updates its Q values. And okay, at the end of each episode, we track the total cost. Remember, cost is just a negative of total reward. And we store this information to monitor how well the agent is improving. There is also a rolling average that smooths out the fluctuations, making it easier to see the overall trend. And I'm looking one last thing, the learning rate and acceleration uh, rate, I mean epsilon, are gradually decayed over time. And this means that at the beginning of training, the agent is exploring and learning rapidly. But as it gets more experience, it slows down the updates and relies more on what it has learned. Okay, and we have get policy. What is that? Um, Once training is complete, this function extracts the best learned actions for each state. It simply goes through the Q table, finds the action with the highest value for each state, and stores it in a policy dictionary. Okay, and here we have evaluate policy, which tests how well the learned policy performs. The agent follows its trained policy for a set number of test episodes, and we track the total reward. And this gives us a good estimate of how effective the policy is in real world scenarios. And okay, that's part done, and example time. So here we set up a test environment in the main block. You can see here. And this is where we initialize our agent with specific parameters like a maximum inventory of what is that 10, and a demand rate of 4, and cost values for holding and shortages. We also set up learning parameters, things like the learning rate, discount factor, and acceleration decay, all of which affects how the agent learns over time. And to make sure our results are reproducible, we set the random number generator. That's okay, and I'm looking, what can I say? Get policy parts, and you can see we call train, which runs full training loop. Here you can see, and allowing agent to learn the best policy over 3000 episodes. And once training is complete, we want to visualize how the agent performed. We plot the episode costs to see how the total cost changes over time, and we include a rolling average to smooth out fluctuations. This gives us a clear picture of whether the agent is improving as training progresses. That's okay, and let's look. We extract the policy the agent has learned using get policy. Then we run evaluate policy where the agent follows its trained strategy for 5000 test episodes, and the total cost is calculated, giving us a measure of how well the agent performs after training. But of course, reinforcement learning only makes sense if it actually beats a traditional approach. So we set up a benchmark policy, and what is that? The order up to policy. This is a common inventory management strategy where we always order up to full capacity no matter what the demand is. We evaluate this policy in the same way and compare the total costs. And okay, that's done. So the results are then visualized in two different charts. And first we compare the ordering behavior of the RL agent versus the benchmark. BM means benchmark, and the purple bars, what was that? Represented the RL policy, while the orange bars show the traditional approach. And what we typically see is that the RL agent is ordering in a more controlled way. It doesn't just blindly restock to full capacity every time. And what can I say? Final parts of code. And we will look at the total cost comparison. This last bar chart shows how much the RL policy saved compared to the benchmark. If the RL model has learned effectively, we should see a significantly lower cost for the trained agent. Okay, and code part is done, and let's look our visuals. And first here. Okay, let's take a look at results and see what we have got. The first plot here shows the training progress, and here blue line represents the episode cost, and as we move through the episodes we can see a clear downward trend. And at the beginning the costs are high and fluctuate a lot, right? You can see here, but as the agent learns, the rolling average, shown in red, steadily decreases and stabilizes. This tells us that the agent is improving over time, finding better inventory decisions that minimize costs. And below the graph, we have the initial cost numbers. You can see here. And the total cost with reinforcement learning policy, our 5,000 episodes, is around 16.4 million. On the other hand, the benchmark policy, the traditional order up to full capacity approach, results in a total cost of 23.6 million. That's a pretty significant difference. The RL policy is clearly making more efficient decisions, reducing unnecessary stock while avoiding shortages. Okay, now let me select the OK switch. Here, this plot compares ordering behavior between the two policies. You can see here the purple bars represent the RL policy, while the orange bars show the benchmark policy. And what's interesting here is that the RL agent tends to order less aggressively, okay? And the benchmark policy often orders the maximum amount, even when it is not needed, while the RL agent adjusts its decisions based on the queue, in this state, sorry. And this means the RL approach is more adaptive. It doesn't just blindly follow a fixed rule, but instead makes smarter choices based on demand and stock levels. I think that's clear. Okay, let's stop here. And finally, the last graph sums it all up, a total cost comparison. And here the purple bar represents the RL policy and orange bar represents the benchmark. And RL policy's total cost is significantly lower, you can see that. And this is exactly what we wanted to see. It confirms that reinforcement learning is not just an interesting experiment, and it is actually delivers better performance than a traditional approach. You can see the values here.